So, welcome everybody to this webinar, which is to run through the contents and conclusions of ICRP Task Group 111's work, which has been posted for consultation for around about 2 months now, I think, and we've got one more month or thereabouts to go. And as I suspect you all know, the topic is individual radiosensitivity, basically. And to make a start, I will share my slides. Great, thanks, Charlotte. So yeah, again, welcome. We'll be talking about the factors governing individual response of humans to ionizing radiation. And as said, this is the culmination of the work of Task Group 111. And this is an opportunity for us to present to you and also take some questions and comments at the end. So if we move on to the next slide, please, Charlotte. Yeah, just to orientate what we're going to try and go through today, I've got a few slides of introduction to explain what's been done. Then we have presentations from the lead authors of all the main sections of the report. So Andrei Wojciech will be talking about early and late developing normal tissue reactions following radiotherapy, followed by Pritha Rajaraman on circulatory diseases, and then Nobby Hamada on cataract, then Claudia Ruber on cognitive impairment. Then two presentations in relation to cancer, Kyoji Furukawa talking about human studies, or epidemiological evidence really, and then Tatsu Imaoka on animal studies and cancer. We have a presentation about the assessment of uncertainty and confidence in the conclusions, and this is, I think, quite important aspect of the report. And it's a move that ICRP has made to incorporate specific consideration of uncertainty and confidence in conclusions in all reports going forward. But this task group is the first to have actually implemented that. So Andrei Wojciech is going to talk us through how that was done and the methodology behind it. And then I will follow on probably just recapping the main conclusions of the report for you before entering an open discussion. These timings, I think, are a bit approximate, but we'll try to keep to time as much as possible. So I hope that's useful kind of orientation for you. So if you could move on to the next slide, please, Michelle. Yeah, so sorry, Charlotte. The membership of the group, I had both the pleasure, I think, and privilege of chairing the group. And you can see the membership here. I'm not going to run through the names. You'll note that two are in grey rather than in black, and that was because Michael Hauptmann and Dan Stram did some useful work and helpful work in the early stages of the task group, but for one reason or another stepped down quite early on. But the others, many of the people are on the call today. And also just note, we had the help from 6 mentees. So we had, it tend to be sort of more junior researchers with an interest and some expertise in the area. And they've been actually very, very helpful in driving forward some of the literature review and assessment to help build the body of the report. So moving to the next slide, Charlotte, please. In terms of reference, I'm not going to read through this. It's been posted on ICRP's website for really quite some time, but it does address, the factors affecting individual radiosensitivity. And then if you step forward again, Charlotte, an important aspect of this piece of work is that it has been review of the literature, the underpinning evidence. There's no consideration of the implications of radiological protection. That is something that will come later, and I'll mention that in a while later on. And then moving on again, Charlotte, please. Just the scope, and you've actually sort of heard this already a little bit when I ran through the order of presentations, that the health effects under consideration listed here: normal tissue reactions after radiotherapy, cancers obviously being the prime contributor to radiation detriment of low dose and low dose rate exposures. The sort of more emerging health endpoints of really quite a lot of concern at the moment in research interest for sure. Circulatory diseases, cataract, and cognitive impairment. And we do, just noting at the sort of second lower part of this slide, consider evidence from a range of different sources. So clinical studies, epidemiological studies of typically larger populations, and supplemented by experimental animal studies and cellular assays as well. If we go another one on, Charlotte, please. So just to sort of give a sort of rationale for why we're doing this, I suppose. You'll be aware that currently the system of radiological protection aims to avoid tissue injury, sometimes or previously known as deterministic effects, and minimize the risk of stochastic effects. So that's the cancers and hereditary effects. And that's done by the sort of key tenets of radiation protection through justification of exposures, optimization of exposures, and ultimately limitation of exposures, which is a legislative sort of benchmark, if you like, or limit that should not be exceeded. But those limits are derived from a notional average that does not really exist, the average in terms of sex and age and sort of underlying population. So the limits are very much population-based, not individual-based. If you step one further, Charlotte, I think an additional line comes into this slide. Oh, no, it doesn't, sorry. But we have the situation has up until now been that it's based on the population. We were asking the question, what is the underpinning evidence to consider moving in some areas potentially to a more individualized approach? The consultation draft, that's, as they've been posted for a little while now, is around about 200 pages of actual text. A lot of references, I haven't counted them all, but there's 56 pages worth. So it's a detailed piece of work, a sort of a thorough piece of work, we hope. That was the intention. Posted for consultation at the tail end of February. And the consultation remains open, and you're at liberty to submit comments through the ICRP website until the 1st of May. And obviously, we've got the webinar today. And if you step on again, Charlotte, I think I've come to the end of my... Oh, no, I haven't. No, sorry. Content. So again, this will be probably quite familiar. Now, this is actually a screenshot of the contents page from the draft report. So you've got the preamble parts, or summary parts of abstract and main points of executive summary. Then instruction and the review methodology. I think it's fair to say, haven't been strictly speaking undertaking systematic review, but we've undertaken very thorough review, which is close to systematic. Elements have been fully systematic, with protocols being lodged with the Prospero database and so forth, etc. And then went through the tissue reactions, be those sort of the early and late developing ones after radiotherapy, or the later developing non-cancer effects of circulatory diseases, cataract, and cognitive impairment. Then the chapter on cancers, and finally a specific consideration of the role of biological sex in modification of responses to radiation, a piece of work which is also supplemented by a much more detailed Annex A down there towards the bottom of the list, because it's an important topic, and a topic that's been much debated in recent years. We have a fairly short section, excuse me, on recommendations for further research, the uncertainty assessment, which I mentioned a little bit earlier on, and then general conclusions to round off. So that's the structure of the report. So hopefully a fairly logical structure, and again, is there for you to read and look through at leisure after today, if you've not had the chance to so far. So I think with that, it's time for me to hand on, and I think next we are going to be considering the clinical responses to radiotherapy. So I'm going to hand over to Andrei Wojciech, who is going to talk us through that section.
Thank you very much, Simon. And Charlotte, could you show the presentation, please? Yes. So the authors of this section, that's Catherine West, was in the audience, and Wei Wei, who was my mentee from China, and myself. Next slide, please. And I will focus on effects induced by radiotherapy. And the reason for this is that, of course, as Simon just mentioned, the system of radiological protection really largely prevents exposure to high doses of radiation that would give tissue effects. An exception is radiotherapy, of course, where the doses go up to 100 gray, of course, very localized. And here you have the data from two studies or two cohorts where you see the numbers of patients in relative terms, in percent, patients who develop grade 2 or higher toxicities. There are some scales, and CTCA is often used. And you see that these are quite significant numbers. So, of course, the question is, why do people develop these side effects? And these side effects can be early, and the early ones, they pass by, but the late effects can be quite serious. They can be life-threatening, and they often require very serious surgical involvement. And that's of course, it would be very good to be able to minimize, maybe not prevent, but at least to minimize and to maybe identify people who are at risk of developing these toxicities. And that the aim of this section was to look at factors that contribute to the development of these toxicities. And we looked at the available literature. Of course, remember that we are looking at clinical studies which are not controlled. They're not randomized. So it's like an epidemiological study. We deal with results that are available. So the conclusions are drawn from the available data. It doesn't mean that they are 100% conclusive, but that's the best what we can do. Next slide, please. And we looked at such factors as cigarette smoking. So first we focus on lifestyle and environmental factors. So cigarette smoking. And it's very interesting, and alcohol consumption, which is summarized on this slide. And it's actually very interesting because you would think that, well, it's obvious that cigarette smoking must increase the risk of toxicities. And indeed, there is evidence suggesting that yes. But remember that these are mainly epidemiological observational studies, so we don't control the exposure. We are not really sure how much people smoked with cessate smoking and so on. But the overall data suggests that yes, if you smoke, you will run a higher risk of toxicities. At the same time, and that's again extremely interesting, there are some cases, for example, pneumonitis, where smoking actually seems to protect you. And the explanation for this is that smoking probably, we know it modulates the immune system. So it weakens the immune system, reducing inflammation. And it may actually have a protective effect. And of course, the conclusion is not that you should start smoking. It's just, it's just interesting to see how complex the etiology of toxicities may be, and how complex the impact of factors that modulate the risk of toxicities may be. With alcohol consumption, it's very difficult to say because most people that smoke also drink, or those that drink usually also smoke. It's also not clear how far and that's also in connection with cigarette smoking, how far the socioeconomic status influences the results of the studies. Because people who have a low socioeconomic status, they tend more to smoke and to drink. And again, similarly, like with cigarette smoking, although alcohol seems to increase the risk of toxicities, there are some reports where red wine, for example, consumption protects against skin toxicities in breast cancer patients. But this was actually a single study, and it's not known whether it's alcohol or components of red wine. Yet studies like this are there again, showing clearly that how complicated things are. Next slide, please. Chemotherapy. Yes, usually, or most radiotherapies are carried out in combination with chemotherapy. And chemotherapy seems to potentiate the risk of toxicities. However, it's not an interaction of chemotherapy drugs with radiation in potentiating, for example, DNA damage, or which we usually tend to think, I think. It seems like we have a biological cooperation, which means that chemotherapy, we know this as well, impairs the functioning of the immune system. So if you have modulated immune system, this may influence the risk of toxicities, again showing the complexity of the problem. Now, body mass index, there are papers suggesting that a low body mass index is associated with increased risk of toxicities. And the reason for this is that people who have a low body mass index, many cancer patients, are malnourished, or they don't eat, eat good enough, and having underweight, having not enough, simply speaking, energy available, increases the risk of toxicities. Next slide, please. Immune therapy seems to have it's probably have an impact on toxicities, but the data are not very clear. I actually thought when we looked into this that there should be a correlation between MHC or HLA genotype and blood group, for that matter, on toxicities, but the results are not there. So it's not really clear whether there is a correlation, although I think that one could expect one, but we simply don't know. We could expect it because we know that the immune system has a strong effect on toxicities. There are some interesting, fairly new studies on the impact of microbiome. There are some hospitals which collect feces from patients who develop side effects or did not, or seem to be protected from side effects. And there are some attempts of transferring feces to change the microbiome of patients to modulate their response to radiotherapy. It's a new field, and the studies are not very large. They're small scale studies, but they're out there. I think this is a field that will develop. Next slide, please. Next slide, please. Yes. Modification by age and sex. Obviously, we know children are generally more sensitive with respect to cancers, but it's not very clear with respect to side effects, although we know that yes, early children or young children develop severe toxicities later following radiotherapy. That's one of the reasons why we tend to use proton therapy and not photon therapy to treat pediatric cancers. But it's a complex relationship. So it's not as clear as for tissue effects as for cancer effects. With respect to sex, females tend to have a higher risk of developing side effects, which is probably not related to any genetic functions or hormonal functions, but there are hypotheses that it's related to differences in pharmacokinetics of chemotherapy drugs. And again, remember that most therapies are combined. Next slide, please. Comorbidities, yes, tend to increase or potentiate the risk of toxicities, such as cardiovascular disease, inflammatory bowel disease. So inflammatory diseases suggest an increased risk of toxicity. Next slide, please. Possibilities of prediction. This is a very, I would say, interesting and debated topic. Of course, we know that patients who have very rare monogenic diseases like ataxia telangiectasia, they develop strong toxicities and also have a risk of radiation-induced cancer. But what is interesting, of course, is whether people who are phenotypically normal have an increased risk. And there have been a number of studies, and these studies are ongoing, on trying to identify tests, both functional tests and genetic tests, to predict. And here you have a list of tests like ATM, nuclear shouting, surviving fraction at 2 gray, or radiation-induced lymphocyte apoptosis. But these tests have not yielded reproducible results. So some publications show promising results, but they could not be validated. So at the end, as of today, we don't have tests which clearly allow to identify patients at risk of toxicities. Next slide, please. And I think that was the last slide. So thank you very much.
Thank you, Andre. That was really clear. So now we can move on to the aspect of circulatory diseases following radiation exposure. And yeah, Preetha is going to cover that topic. So over to you, Preetha.
Okay, great. Thanks very much. So moving now on to the later effects, as Simon had noted earlier on. One of the areas where there has been increasing evidence of greater risk is with diseases of the circulatory system. Next slide, please. And given this background that over the last decade or so, there really has been growing evidence that ionizing radiation could increase the risk of various diseases of the circulatory system, the scope of our particular subgroup within TG111 was to evaluate if there is potential susceptibility with respect to radiation-related effects for these diseases, and also to assess what is the strength of evidence for these potential modifiers. Next slide, please. Here, again, I won't list them out, but you see the many people who contributed to this, not only the writers that you see on the left-hand side, but also a number of reviewers who gave us very thoughtful, very detailed input that made it into the chapter. So again, thanks to everybody who contributed, including 3 mentees who wrote parts of this review. Next, please. So when we think about diseases of the circulatory system, it almost seems strange to lump that together as one outcome because it is such a diverse set of outcomes. As you can see on the slide here, these are just the major categories within the ICD-11, and those break out into subcategories such as myocardial infarction. And it's quite likely that there are different underlying mechanisms of disease for each of these subtypes. So when we are trying to understand risks, we do need to take into account that this is really a very heterogeneous group of diseases. And compounding that, the actual system of classification has changed over the years. So when we are comparing studies from different time periods, this can be a little bit challenging because you're not always comparing the exact same outcomes if the disease classification has changed between those studies. And finally, in terms of which organ dose do we use to assess risk? Again, not always very clear in terms of which are the target organs for that underlying biomechanism for each of these different smaller outcomes. Next slide, please. So let's look at the body of evidence really for the main effect of radiation on disease of the circulatory system. And increasingly, I think it's quite accepted that at higher doses of radiation, there are clear indications of effects on various diseases of the circulatory system. And a lot of this information comes from various studies of cancer survivors, whether that is childhood or adult cancer survivors. As I had mentioned before, over the last decade or so, there's been growing evidence that even at lower doses, we are seeing some evidence of higher risk of various diseases of the circulatory system. Certainly in studies of atomic bomb survivors, we have seen increased mortality risks for heart disease, hypertension, stroke, valvular heart disease, hypertensive organ damage, as well as heart failure. But also in large studies of nuclear workers, there have been increased risk for all circulatory diseases combined, as well as cerebrovascular and ischemic heart disease. Finally, in certain chronic environmental exposure settings, we do also see increased risk overall for combined circulatory disease as well as ischemic heart disease. Now, I will note that at these lower doses, the evidence is more mixed, and there are certainly other studies where the effect is unclear or we don't see effects at all. Next, please. So moving further from the main effect, our charge was to think about, are there susceptible groups within these larger studies which are potentially more at risk when it comes to radiation exposure? And this comes with its own set of challenges. Certainly, if we are thinking about studies that have high quality individual dose estimates, as well as detailed data on potential modifiers, those are a small set of studies in the end. Again, thinking about the particular outcome, diseases of the circulatory system, the effect size, the actual risk that we would expect to see is much smaller compared to, say, risks for cancer. And so that, again, limits perhaps our power to detect this in smaller cohorts. Certainly in individual studies, some combination of smaller study sizes, a limited number of the actual outcomes, particularly once you start breaking it down into disease subgroups, narrow ranges of radiation dose. So if you think about it, many of the occupational studies are on really the lower dose side, whereas the therapeutic doses are on the much higher dose as range, as you heard from Andre. And so comparing those two, you don't really have overlap in that dose range. And similarly, I think this is true of potential effect modifiers as well. So if you just think of age at exposure, again, the age range that you're looking at for childhood cancer survivors is very different from the age range you're looking at in occupational studies. Next slide, please. So despite all of these messiness, we do actually see some patterns emerging. And so we really looked at these potential modifiers of risk in terms of those that are intrinsic, i.e. those factors that it's really very hard for us to change, whether that is age or sex, gender, our genetics, versus those that are of greater risk with younger age at exposure in both breast cancer survivors, as well as Hodgkin lymphoma survivors and Tetra River residents. Of course, there were other studies where we did not see this. In terms of attained age, this was a little bit weaker in terms of evidence, but we did see some suggestion of a possible decreased risk with greater attained age in MIAC nuclear workers, as well as in the Tetra River cohort. Again, in other medical, occupational, or environmental studies, we didn't see very clear patterns. Next, please. Moving on to biological sex, here we did see some degree of consistency where there was higher risk in females, certainly for incidence of myocardial infarction and possibly mortality from heart disease and valvular disease in the atomic bomb survivors, as well as combined circulatory diseases, as well as ischemic heart disease mortality in nuclear workers. Again, there were other studies where we didn't see this very clear pattern. Moving next to genetic factors, which of course are of great interest to many of us. There have been a few small studies in childhood cancer survivors that suggest some very interesting methodology where you can use polygenic risk scores from single nucleotide variants, common SNVs, to try and detect radiosensitive groups for outcomes such as stroke and hypertension. And while I think the approach is very promising, So far, it hasn't been replicated, but certainly something that is worth looking at in future studies. Next, please. So moving on now to the extrinsic factors. These are factors that could be changeable to some degree. The place where we saw the most consistent modification of risk was with anthracycline exposure, usually in a detrimental direction in cancer survivor studies in both childhood and adult cancer survivors for various outcomes, including all cardiac disease, heart failure, coronary artery disease, as well as valvular heart disease. But of course, there were other studies that did not observe this modification. And we saw no consistent patterns for other chemotherapeutic agents, even though several of these studies had looked at different classes as well. In terms of smoking and alcohol use, there were fewer studies that had very good data to be able to look at this. But that said, we really didn't see any clear effects for either smoking or alcohol. Next, please. Moving to the animal studies, there are some animal studies that have assessed the role of strain, sex, age, lifestyle factors, and co-exposures on the circulatory system response to radiation. And these have been mainly focused on cardiac function. And rather than going into this in great detail, I'll just say that the results were broadly consistent with what we've seen in human epidemiological studies. There were various chemotherapeutic agents that seemed to somewhat convincingly modify radiation-related risk. Female animals did appear to be more sensitive to radiation. And unfortunately, there were only a few studies that were able to look at age exposure. So the nature of that interaction is unclear from animal studies. Next, please. So then putting together the evidence from the epidemiological data as well as the animal data, what we saw is that there are some groups that seem to have increased susceptibility. Certainly co-exposure with chemotherapeutic agents, particularly the anthracycline compounds, younger age at exposure, and female sex. However, large uncertainties still remain regarding the nature of these relationships, particularly once you start looking at more specific disease outcomes within diseases of the circulatory system. And this really calls for the need for further assessment of these potential sensitivities, particularly in studies that have a wide range of radiation doses, ages, biological sexes, and detailed information on potential effect modifiers. Next, please. So I'll just finish with this slide, but not talk too much about it because I know that you'll hear much more from Andrei Wojcik, other than to say that we did also do an uncertainty and confidence assessment on the results of our analyses. And as you can see here, really the bulk of the evidence falls in that greenish, reddish area where there's some evidence, but it's really not very strong yet for agent exposure, biological sex, and chemotherapy, particularly anthracyclines. So I think that is my last slide, but if you could just move on, please. Great. Thanks very much.
Great. Thank you very much, Preetha. Again, very comprehensive. And just to note that the animal work was looked at largely by Nobi Hamada and some of the mentee groups that Preetha mentioned earlier on. So now, in fact, we're going to hand over to Nobi Hamada, who led the section in relation to cataract. So Nobi, over to you.
Thank you very much. Charlotte, could you please show the slides for me? Thank you very much. Thank you. Next slide, please. So ICRP has listed cataracts over the last 7 decades and has recommended the dose limits since then. And since publication 1, ICRP has considered that the lens is among the most radiosensitive organs. And in 2011, ICRP recommended a threshold of 0.5 Gray, and at a higher dose, there is emerging, although limited, evidence for elevated risk of normal tension glaucoma in Japanese atomic bomb survivors and Russian Mayak nuclear workers. So, a conclusion in 1984 remains unchanged that the lens is the most radiosensitive ocular structure. So, a focus today shall be placed on cataracts. Next slide, please. So we have conducted a systematic review, and at that time, this was done with mentee Steve Barnard from Public Health England as a mentee, and myself. So table 2.9 in the draft lists human epidemiological studies, such as in the atomic bomb survivors, US radiological technology cohorts, and the Mayak workers, Chinese high natural back radiation area residents, and astronauts. And table 2.10 lists experimental studies, mostly in vivo studies using all rodents, and 5 in vitro study using a lens epithelial cells of a human or bovine origin. So there is no consensus about the various potential effect modifiers, but a brief outline is given below. Next slide, please. So for the heritability, so evidence within the human population is limited. And it is well known that germline mutations of certain genes such as lens-crystallins or connexins, gap junction proteins, underlie congenital cataracts, but its relevance to radiation response isn't known. And the white skin tone is somewhat associated with higher radiation risk than other tones in the US radiological technologists cohort, or certain single nucleotide polymorphisms of ADM, ataxia-telangiectasia mutated, and p53 tumor suppression increased radiation risk in Chinese high background residents. Next slide, please. For age, so high radiation risk is seen at the young age at exposure in A-bomb survivors and higher attained age in Mayak workers. And the younger age at exposure tends to cause higher incidence in animals, although the age response varies in a not straightforward manner. And the rat exposed at the older age had a higher progression rate, but those at a younger age had a shorter latency and a high incidence. For biological sex, epidemiological data shows a higher risk in Mayak females, but in AHS, male has had a higher risk. And in animal studies, so in rats, so higher incidence was observed in the males after lower radiation, but this was opposite after higher radiation. Next slide, please. So for lifestyle comorbidities, etc., so high radiation risk was observed in the diabetics and some cohorts, and the less evidence available for diet, smoking, etc. So hormonal effects. So this was observed in the animal models, the first in rats. So cataractogenesis and ovary ectomized, so ovary removed rats, was promoted by pre-radiation administration of estrogen, but oppositely spared by post-radiation administration. And radiation cataractogenesis did not occur in pituitary removed flags, but occurred in flags with pituitary hormone replacement. Next slide, please. So for the immune system, this should play a very limited role because lens capsule prevents the immune cells from entering the lens, and the role of a persistent inflammation is known. And for genetics, so mice who are insufficient for ATM, RAD9, BLAC1, and other genes show increased sensitivity to radiation cataracts. And humans, certain SNPs of ATM and the p53 has been reported to increase radiation risk in Chinese high background residents. and that the role of epigenetic factors hasn't been reported yet. Next slide, please. I think this is the last slide. So potential effect modifiers include sex, age, and genetics, along with potentially important roles of comorbidity and co-exposures, but no firm conclusion can yet be reached. The further studies would be needed. And for predictions approach, radiation catalactogenesis is considered attributable to mechanisms other than cell killing, and really biomarkers or bioindicators haven't been identified, but ADM differentiation potential and a crystalline oxidation may be useful markers. And unlike other structured spatial temporal catalactus changes can be monitored almost non-invasively. I think this is the last slide. Thank you.
Many thanks, Nobby, for covering the cataract section. So moving on to the final part of the non-cancer disease area, I'm going to hand over to Claudia Ruber, who covered the topic of cognitive impairment. So Claudia, over to you.
Thank you, Simon. Yes, yes, I focused my literature research on radiation-induced brain injury and leading to cognitive impairment. First or second slide, please. So first evidence of age-dependent effects of ionizing radiation on cognitive functions come from different cohorts with low to moderate doses to the brain. And here the most important cohorts were the atomic bomb survivors, the tinea capitis cohorts, and the Swedish hemangioma cohorts, showing clearly, yes, effects on the cognitive impairment. But there are also other studies analyzing very low diagnostic doses, showing no detectable cognitive effects. Next slide, please. Clinical evidence of age-dependent effects on cranial radiotherapy come mainly from childhood cancer survivor studies, showing that younger age at radiotherapy is a very strong or even the strongest risk factor for neurocognitive impairment. And especially children below 7 years old show most severe and lasting IQ decline. And the most important data come from prophylactic whole brain radiotherapy in children with acute lymphatic leukemia, showing a clear IQ drop, especially in the very young children. But we have to say that actually modern radiotherapy approaches largely abolish these age-dependent effects. So radiotherapy has improved extremely in the last decades. So now I think it's not such a worth effect of radiotherapy. Next slide, please. The clinical effects of age-dependent effects of cranial radiotherapy in adult cancer survivor is not so clear. I mean, most data come from low-grade glioma patients because these higher-grade gliomas have a really very bad prognosis, so you can't study long-term effects. But in these low-grade glioma patients, you can observe a progressive cognitive decline over years. And especially interesting to analyze the effects of irradiation itself are these prophylactic whole brain radiotherapies, for example, for small cell lung cancer or for total body irradiation, showing that there's an increased risk or cognitive risk in long-term survivors. But there are no proven age-related differences within the major adult brain. So it doesn't really matter if you're 30 or 60 years old. There's no clear difference. Next slide, please. there are multiple animal studies analyzing the pathophysiology, and there are clear key mechanisms of radiation-induced brain damage. For example, hippocampal neurogenesis is very radiation-sensitive because these neural stem cells, for example, in the subgranular zone of the hippocampus, are highly radiosensitive, and even low doses eliminate these neuroprogenitors, leading to reduced adult neurogenesis. And even low doses such as 10 milligray triggers apoptosis, especially in the embryonic brain. And because immature brain contains much more proliferating cells, there's a much greater damage after exposure to ionizing radiation. And also there's a shift from neurogenesis to gliogenesis after repeated ionizing radiation. And these effects persist for months to years after irradiation and impair memory and learning. Next slide, please. Another key mechanism is the neurovascular damage. So ionizing radiation disrupts blood-brain barrier integrity, leading to endothelial apoptosis with vascular leakage. And endothelial cells develop a pro-inflammatory phenotype with cytokine and chemokine secretion. This leads to an immune cell infiltration, enhancing neuroinflammation. And this long-term vascular damage leads to tissue hypoxia and metabolic impairment, and leads to cerebrovascular complications like stroke months to years post-irradiation. Next slide, please. And another key mechanism of this radiation-induced brain damage is a chronic neuroinflammation. Microglia and astrocytes are the key inflammatory mediators because they react to damaged cells which release debris and prime these local glia cells. And this leads to a chronic glia activation with a vicious cycle for neurodegeneration. And in general, neuroinflammation drives permanent cognitive decline. And again, this age dependency is very important because immature brain has much higher proportion of radiosensitive progenitors, and this leads to increased cell loss and amplified neuroinflammation after exposure to ionizing radiation. Next slide, please. So in conclusion, we have a clear age dependency. We can describe a multifactorial pathogenesis. We can also say that modern radiotherapy approaches can reduce these risk for cognitive impairment. And at the moment, there are some studies about hippocampal avoidance, which are expected to significantly reduce these adverse neurocognitive outcomes. Next slide, please. But there are still open questions. And yes, for example, the exact pattern mechanism of radiation-induced cognitive syndrome at the molecular and cellular level are still incompletely understood. At the moment, there are no effective prevention or long-term treatment modalities, especially molecular therapies targeting neuroinflammations are urgently needed. I think a very interesting question is whether radiotherapy in adulthood predisposes these patients to neurodegeneration in old age. Moreover, it's not clear at the moment these new radiotherapy approaches, such as particle therapy, guided radiotherapy, what is the effect of these new irradiation approaches. And of course, it would be very beneficial to have biomarker for the early identification of at-risk patients. So I think this was the last slide, just the note of thanks. I would like to thank for your attention. And of course, I would congratulate Simon for his many years of patient and successful leadership of this working group. Thank you.
Well, thank you very much, Claudia. And clearly, it's not possible without the contributing authors. So thank you for your, each of your contributions. Now, we're moving the focus to radiogenic cancers. And Kyoji Furukawa is going to talk us through some of the underpinning epidemiological evidence. So I can see you've got your slides up, Kyoji, so over to you.
Hello, I'm Kyoji Furukawa. I'm going to talk about some evidence from human studies on cancer. Radiation related to cancer is a central issue in radiation protection, and our current understanding is largely derived from epidemiological studies, including studies of airborne survivors, as well as medically, environmentally, and occupationally exposed cohorts. From these studies, we consistently observe dose-response relationship, which basically supports causal link between radiation exposure and cancer risk. Importantly, there's a substantial risk variation between individuals. Understanding such variation is crucial for radiological protection and decision-making, for example, in medical settings. Potential effect modifiers that are reviewed in this report include sex, age, sex, smoking, other lifestyle factors, underlying conditions, environmental factors, genetic, epigenetic factors. In evaluation of these factors, risk is typically quantified by excess relative risk and excess absolute risk for various cancer incidence or mortality outcomes. Sometimes it is very difficult to understand the difference. Sometimes we see the significant effect modification only for one of ERR or EAR. And also important, most of the human evidence for effect modification comes from the lifespan study of airborne survivors because it provides a large, well-characterized cohort of a general population of all ages and sexes with accurate dosimetry and long-term follow-up. So these characteristics allow a more reliable estimation of radiation risks and effect modification in comparison to other studies. Age is one of the most important modifiers of radiation-related cancer risk. This shows a typical age risk pattern observed in all three cancer mortality data in the lifespan study. This clearly shows younger age exposure generally leads to higher cancer risk, and ERR decreases over time with increasing attained age, while EAR increases with age. This observation is supposed to be largely due to increasing baseline cancer rates over time. The magnitude of the age effect varies across cancer sites, with stronger age dependence observed for some cancer sites like leukemia, thyroid cancer, and breast cancer. So basically, age is one of the strongest and most consistent modifiers for cancer risk, radiation-related cancer risks. And the risk depends on both age exposure and attained age, with some variation among cancer sites. Biological sex is also a relatively consistent modifier of the radiation-related cancer risk. In the lifespan study, the sex difference is clearer in ERR, with female risk being higher than male risk, but the difference is less consistent in EAR. The sex difference is also varies by cancer site. For some sites like stomach, lung, thyroid, and also breast, risk is higher for females. And for other sites such as leukemia EAR, risk is higher for females, for males. However, limited or inconsistent evidence are reported from other studies, like environmental occupational cohort studies. Overall, sex is a robust modifier, but underlying mechanisms are not fully understood. Plausible contributors for the sex difference may be sex variations in baseline rates, age distribution, cancer types, and other hormonal biological factors. How about smoking? We know both smoking and radiation independently increase the cancer risk, particularly for lung cancer. About interaction between smoking and radiation for lung cancer. The interaction effect appears to be rather complicated pattern observed in the lifespan study, which is described something like this. It is the interaction, radiation-associated lung cancer risk appears to be largest for smokers who are smoking moderately or lightly. And there's almost little or no radiation-associated excess risk observed for heavier smokers. In other studies, observations are not very consistent or limited for the interaction effect. And for most other cancer sites other than lung cancer, smoking has little impact as a risk modifier. Overall, smoking is a major, well-established modifier, but the interaction effect with radiation is complicated and not fully understood. Reproductive history, such as Asia menarche, has been also known to modify the effect modify the breast cancer risk in the lifespan study. This is a main result. The risk significantly increases with decreasing Asia menarche, and Asia exposure effects are highest around Asia menarche. These observations suggest highest breast sensitivity during puberty. Key message is overall reproductive factors appear to be important modifiers, but mainly for breast cancer and other hormone-related cancers. And evidence suggests increased radiation sensitivity during hormonal development. For other factors, basically available evidence is quite limited or inconsistent. There are many plausible mechanisms about risk modifications, but human evidence for most of the potential modifiers is weak and inconclusive. Summary for my presentation. Only a limited number of modifying factors appear to have robust epidemiological support. The most robust evidence exists for age exposure and biological sex. There's a moderate evidence for smoking in lung cancer risk and reproductive factors such as age menarche for breast cancer. In contrast, evidence for the other potential factors, including genetic, hormonal, other lifestyle factors, remain limited. This is possibly due to limited statistical power and also incompleteness of data, such as measurement error, missing data, and also heterogeneity. As a result, predicting of individual cancer risk is still challenging. Okay, that's all for my presentation. Thank you for your attention.
That's great. Many thanks, Kyoji. A very large amount of evidence that had to be trawled through to come to that point. And again, thanks for taking the time to do that. So moving to the sort of other main aspect of cancer studies that we looked at, Tatsu Imaoka is going to talk through the evidence base from experimental animal studies. So Tatsu, over to you.
Yeah, thank you very much. I'm Tatsu Imaoka, and in this task group, I covered the experimental animal studies on cancer. So I'm today privileged to have the opportunity to present the main evidence drawn and conclusion drawn. So this slide shows the role of animal studies. So information obtained from animal experiments can be used to complement epidemiological evidence because there is smaller likelihood of uncontrollable biases in animal experiments, and also because there is opportunity to examine a wide range of modifying factors compared to epidemiological studies. So we systematically reviewed the available evidence from animal studies on modifying factors of radiation-related cancer. So in this review, we evaluated each of the literature and used only those studies reaching a certain level of reliability. And so first is the age and sex. Regarding the age and exposure, there are general tendency in that young animals are more susceptible than fetuses or adults, with some variation between tissues. So as shown in the table, so this table summarizes important evidence. And in most cancer sites, neonatal or young animals are more susceptible. But there are some cancer like that of the breast showing peak susceptibility at the peripubertal age. And there are some other showing different tendency. So that is that. And regarding attained age, there are very few studies examining the effect of attained age in animal studies. But these small numbers of studies indicate that ERR generally decreases and ERR increases with attained age. it so you can see the tendencies like this, and these tendencies are pretty much consistent with that you observe in epidemiological studies. And regarding the sex, females are more susceptible in general to all solid tumors like and lymphomas. So in this table, you see that the male to female ratio for the ERR of all solid tumors is 0.5, indicating that females are more susceptible. And also you can see the same tendency in another study. And males are sometimes susceptible to other types of cancers like mild leukemia, as shown here, and other like tumors like liver tumors. Regarding the lifestyle factors, there are several studies examining the effect of cigarette smoke in animals. And these studies showed a superlative, or at least an positive effect on interaction between radiation and smoking. And body weight also it's shown to increase radiation-related tumors in various animal models. In these models, body weight increase was induced by increasing the amount of food or the proportion of carbohydrate or fat. And they all indicate that this diet increases both the body weight of the animals and the radiation-related risk of cancer. And female sex hormones are not lifestyle factors, but it is known that reproductive history is closely related to female sex hormones, and we can assess the effect of hormones directly in animal studies. And these studies showed that estrogens are generally positive or enhance the effect of radiation in inducing cancer, but other class of hormones, which are mainly anti-estrogens like tamoxifen and weak estrogens, these hormones are have negative impacts on radiation-induced cancer. So these lines of evidence supports that female sex hormones increase radiation-related risk of breast cancer in animals. Regarding the underlying conditions, we did not see any studies on diabetes or collagen vascular disease, but we found some animal studies assessing the interaction between radiation and induced inflammation. And these studies indicated an increased risk of cancer in some organs. So there is some evidence indicating that inflammation increases the risk of radiation-related cancer. So, or other environmental factors. So there are very few studies dealing with the UV and sunlight, and these studies indicate that there is some increase in cancer. And there are lots of studies assessing the interactions of radiation and chemical carcinogens. And here we classify the chemicals in two classes, alkylating chemicals and adduct-forming chemicals. And these are chemicals are essentially mutagens or genotoxins. And these chemicals are generally additively working on radiation-related risk in animals. But there are some chemicals that are protective. So there are many studies assessing the effect of radioprotectors and antioxidants, and some food ingredients like fiber or extract from plants. And many of these chemicals are protective against radiation-induced cancer. DNA repair deficiencies increase, decrease, or have no effect on radiation-related cancer depending on the affected gene and tissue type. So there are some evidence suggests that defect in the genes related to homologous recombination repair increases the susceptibility of the animals to radiation-induced cancer, but it depends on the models. And in some cases, these deficiencies in gene function decreases radiation-induced risk of cancer. So there is a strong dependency on the type of affected genes and tissue. And animal strain influences radiation-related cancer, but it is there is a very complex pattern. And for example, regarding the induction of thymic lymphoma, the C57BL6 strain is more susceptible than the C3H strain, but in other cancer sites, the relationship is opposite. C3H strain is more susceptible than C57BL6 strain. So the strain influences radiation risk, but in a tissue-specific manner. And there are many models, animal models, or mainly mouse models of cancer predisposing mutations. And these include TP53, CDKN1, P10, APC, PATCH1. These are all models of hereditary tumor syndrome. And in these animal models, it is generally observed that radiation acts stronger than in wild-type animals. So this is my last slide. Younger age at exposure increases the risk of all solid tumors with variation between tissues. Attained age decreases ERR and increases EAR for all solid tumors with variation between tissues. Female sex is associated with higher radiation-related risk for all solid tumors with variation between tissues. Cigarettes from smoke increases radionuclide-related lung cancer risk. Body weight increases radiation-related risk for all tumors and for some specific tumors. Female sex hormones increase radiation-related risk of breast cancer. Chemical carcinogens generally increase, whereas some protective chemicals decrease radiation-related cancer. But there we should add that qualitative evidence is limited. And genetic factors influence radiation-related tumors in a tissue-specific manner, but again, quantitative evidence is limited. So that's all. Thank you for your attention.
Many thanks, Tatsu. And I think what we have with the two presentations we just heard is a nice demonstration of the complementarity between human epidemiology and experimental animal and other experimental studies in sort of developing evidence bases and helping to interpret them. So now we're moving to an aspect which is sort of starting to draw things together. And first, I'd like to return to Andrei Wojciech to talk through the approach that was adopted to assessment of uncertainties and competence in the conclusion. So, Andrei, over to you.
Thanks very much again, Simon. What I would like to quickly show you is the outcome or progress of work. Actually, we are not finished yet, of a working party of ICRP on uncertainty. The person who has initiated this working party is Dominique Laurier from ARSN in France, who has been since a long time saying, well, we have to, in ICRP, when we produce our reports, we have to include statements on how certain are we that the conclusions that we draw are solid or not solid. Well, what's the basis? What is the certainty or uncertainty? And here you have a list of contributing authors or members of this working party. And it's Kim Applegate, who was the chair of C3 until recently, François Bocheux, who leads C2, Mijaki Kai, who has been a member of Main Commission until recently, then Dominique himself, who chairs C1, Thierry Schneider from C4, and myself. Next slide, please. As I said, what we really want to achieve is to develop guidelines how uncertainty should be presented in the reports. So we have identified some general questions that we would like to answer. So the first one is how to better take into account uncertainties while keeping it simple. How to improve transparency, and how to improve communication transparency about what is our knowledge, what do we know, what don't we know, and communication, how do we communicate the uncertainty. And there are two approaches that we have followed. One is from the APCC matrix. APCC stands for Interdisciplinary Panel of Climate Change, or International Panel of Climate Change, and the Powell's Principle, which I will take you through in the next slides. Next slide, please. The IPCC, or Intergovernmental Panel on Climate Change, is an organization that, yes, deals with climate change, as is obvious, and you will know that climate change is a debated issue. Well, we have no doubt that the climate is changing, but the thing is, what factors influence it? Do we at all have the possibility to influence this? Can we stop the changing? And so on. And so they developed guidelines. Next slide, please. On how to present what we know and what we don't know. And they used the approach, or they built something, or they recommend building a matrix that you see here on the right side. And it's a matrix that summarizes agreement and evidence. Now, evidence, let's start with evidence, is it describes what amount of data we have that, again, in connection with TG111 would be, what is the risk modifier? What amount of data do we have on a particular risk modifier of developing radiation-induced cancer or developing radiation-induced toxicities? And the evidence can be limited, medium, or robust. And we, as the authors, agree on which category of evidence we are dealing with. And then we have an agreement, and that's about, it's about the knowledge that we have on the factor that we are dealing with. And here, the interesting question is, whose agreement is this? Is this the agreement of the scientific community, or is it the agreement of the experts? And it's obviously the agreement of the experts, because we know that one of the elements, basic elements of science, is that we disagree with each other, or we debate. It's the driving force of science. We disagree, we point to open questions. So, but at the end of the day, in this connection, we have to come to an agreement. And so it's the agreement of the experts. And here we go for high, medium, or low agreement. And if we have defined the agreement as the evidence, then this translates into a vector that you see on the bottom of the slide, and that's the confidence scale. Obviously, if we have robust evidence and high agreement, then we have very high confidentiality that our statement is correct, or it's a strong. We can be confident in that we are right. And opposite, if the evidence is limited and the agreement is low, then the confidence is very low. And I will not show you examples because Simon will show you an example. Preeta actually also showed you an example of the application of this approach. But next slide, please. I want to rather show you a second approach that we discuss and we recommend. And now that's the working party on uncertainty for cases where you cannot really use this matrix approach of IPCC. And here we take example of Colin Powell. Colin Powell, some of you will remember, he was Secretary of State under President George Bush Jr., who at the time of his presidency was regarded as a cowboy type, but now he seems to be a statesman. So that's how things change. So Colin Powell defined principles of how to communicate risk, or how to, well, not risk, how to communicate what we know. He said you have to be very clear in order to be transparent and to be trusted. You need to clearly define what you know, what you don't know, and what you think. And this is the approach that we recommend. Next slide, please. And I will just give you an example. The IPCC approach will be presented by Simon in the next presentation. But here is an illustration of how Powell's principle is used in TG119. And TG119 is on diseases of the circulatory system. And this slide was given to me by Dominique Laurier, and he agreed to show this. It's preliminary, but it just gives you an example. So here you have what we know. We know that there is evidence for excess risk of diseases above certain doses. We know that there is growing evidence for dose response relationship below 500 milligray. We know that there is a relationship for observed effects, and there is heterogeneity in estimated risks. However, what we don't know are what the mechanisms are. We don't know what are the target organs. We don't know what is the variation between sexes and age. And so we don't really know, is there a threshold? Yes, no. And then we say, well, what do we think? Based on what we know and what we don't know, this is what we think. And we think that recent findings confirm the risk of disease. The current classification needs to be reconsidered, and so on and so forth. Again, it's a way to present very clearly our state of knowledge. And when we give recommendations about, or when we draw conclusions from data, it should be very transparent what conclusions are based on evidence, what we know, what we don't know, and what conclusions are based on what we think. I think that was the last slide. Thank you very much, and it's back to you, Simon.
Yeah, thank you, Andre. And I'm just going to sort of wrap up the presentational part by running through a few slides, to some extent reiterating what you've heard already. So yeah, thank you, Charlotte. If you put the remainder of my presentation up. Yeah, so I've got a few slides with the main points of the report. These are taken verbatim from the draft that's posted. And I say there's nothing really new here because you've heard it all in more detail already. So firstly, there is robust evidence for the severity of normal tissue reactions to radiotherapy being influenced by some genetic factors, the monogenic disorders that Andre mentioned, concurrent chemotherapy, comorbidities listed out there, and age. There's some evidence to support a role of smaller genetic changes, such as the single nucleotide polymorphisms, or SNPs, as they're usually called, in some genes. Prediction of the normal tissue reactions using cellular and other assays has been reported, but it remains unclear if prediction is really possible in a widespread clinical, translatable, transferable way. For circulatory diseases, concurrent chemotherapy with anthracyclines may influence risk. Convincing evidence in relation to other factors is lacking, but age and sex may influence the likelihood of certain circulatory disease outcomes. And the investigation of prediction of individual response has yet to be conducted. Moving on to the second slide, or the next slide, please, Charlotte. So there's only limited evidence available in relation to cataract risk. Some evidence suggests that concurrent diabetes increases risk. Investigation of prediction of individual responses has not been conducted. In relation to cognitive effects, there's robust evidence for age exposure influencing risk, with those exposed at younger ages being at greater risk. And investigation and prediction of individual response, again, has not been conducted to date. In terms of the cancers, radiogenic cancers, we've got robust evidence indicating that risk is influenced by age exposure, with the younger ages generally being at elevated risk, with some variation between sites. Biological sex, in terms of excess relative risk, females are generally at greater risk, but again, variation between cancer sites. Smoking, and there's the notable data from the radon lung cancer studies, risk tending to be higher, but Kyoji noted the complex relationship between smoking and radiation risk in the Japanese A-bomb survivor groups. Some evidence exists for genetic factors and female sex hormones influencing risk. And then finally, the prediction of radiation cancer risk by means of simple tests has not been convincingly demonstrated to date. And the final slide with the main points. So the next one, please, Charlotte. And really, this is the overall summary, I think, the overall point, which is our final main point within the early parts of the report. Overall, only limited robust evidence is available on the influence of specific factors on responses to radiation exposure. The most secure evidence is in relation to age and biological sex, particularly with respect to radiation-related cancers. And the ability to predict responses at the individual level remains a significant challenge. So those are the sort of bottom lines of the work that we've carried out. Just to expand a little bit on the uncertainty confidence thing, Charlotte, please, next slide. That Andre was presenting the methodology behind. You can see the matrix to the left there, based on the Intergovernmental Panel on Climate Change methodology. Again, a table taken from our draft report, which sets out the factors that have been examined, age of exposure, attained age, biological sex, and so forth, giving the assessments of the evidence level, robust through to limited, and the agreement high through to low, and then the resulting confidence ranging from very high down to low, although we actually have no lows in this list here. So you can see we are, as a collective group, task group, we were very confident, had high confidence in the data relating to age exposure and attained age and biological sex, also smoking. But for the other factors, genetic factors, we've got a reasonably high level, but the remaining factors listed here, the comorbidities, alcohol consumption, obesity, and female sex hormone, the confidence was assessed to be medium. And I think this partially is probably a reflection of the amount of evidence available on these other factors. But this is the current state of play as we've interpreted the literature, having had a very thorough look through the literature on what we know and sort of what we don't know about the factors that impact on individual response to ionizing radiation exposure for the health endpoints we've discussed. I think I've got one more, perhaps possibly two more slides. So Charlotte, can you do the next one? Oh yeah, a couple more actually. So as the work's been going on, it's been going on quite a long time. We started back in 2020 or perhaps even a bit before. A number of reviews have been published in the open literature, and these are listed out here. One or two have been cited, I think, by colleagues as we've been going through. So in a sense, we were sort of adopting the approach of trying not to land any huge surprises on everyone, although not everything's been published that you've heard about today, for sure, and not all aspects of the draft report as it stands is likely to find itself into individual standalone publications, but there are some. And the next slide, please, Charlotte. Yeah, just to note that while the work of Task Group 111 examining the underlying evidence is nearing a conclusion, there's another task group, Task Group 128, which started relatively recently back in 2023, which is taking the next step, really, sort of asking the questions, given the evidence we have, are there implications of the evidence for the system of radiological protection overall? Are there significant implications, and should there be some consideration of the application of a more individualized or stratified approach in the future? So it's a task group that started a couple of years or 3 years ago under all of the 4 constituent committees of ICRP. And in the course of the work being undertaken by this task group, there'll be an open meeting prior to publication, which we didn't manage to achieve for Task Group 111, just this consultation stage seminar. And much of the focus is on the medical sector, and I think this is reflected in some of the questions that have come up through the chat function there. So with that, I believe we've come to the end of us talking at you, if you like. So thank you again to all contributing authors and presenters today. It was great work, and it's been great working with you all. But now I think we're happy to sort of collectively take questions either through people raising hands, should you wish, or we can start looking through the questions that arrived in the Q&A bar. So I will have a look at that in a second, and maybe a request that some individuals from our speaker panel address different questions. So I'm just going to, I think, the earliest in time questions as they're displayed on my screen. So Martin is asking about the childhood IQ decrease and whether this was controlled for the time lost to attend school while undergoing the cancer therapy treatment. And Claudia, I don't know if you're able to comment on that. Oh, I'm not. Whoops. I'm not hearing Claudia at the moment. Anyway, actually, one thing I omitted to say is that if we're not able to answer questions here and now, we will follow up by some written responses in the future. Next question is DRL levels, which I think are dose reference levels. I think that is something that's not specifically addressed in our work, and I would suggest you look at relevant ICRP reports to find those. I think there are differences between different countries sometimes. Rick is asking about the possibility that the factors we've been discussing today will be included in the next ICRP recommendations to begin, whether they begin to impact on practical protection. Well, I think the answer to that is really that is the work of Task Group 128, which is at a relatively early stage, as mentioned. So I think it's a case of wait and see, but I think you have heard that there are only a limited number of factors where we have the competence to actually do anything, and primarily age and sex. So you're not going to be seeing a fundamental change into trying to assess an individual in terms of all their co-exposures, for example, or their background medical history, etc., etc. But as I say, this is something that will come out in due course. Some anonymous questions. I'm not sure what RNA expression values relates to. Sorry. What about the possible radioprotective of DMSO? So this, I think, is likely to have come up through animal studies. So, Patsu, have you got any comment on that? Did you find anything on DMSO?
No, I did not find the effect study using DMSO.
Can I comment, Simon? Because
Sure,
there's very
course.
clear evidence from cell experiments, but it
Yes.
has really no relationship for radiological protection, I would say.
Yeah. It's actually quite toxic, if I recall, isn't it? So no animal evidence, good cellular evidence. So that's the state of play there. So question from David: would it be fair to consider enhanced risks to circulatory systems when reviewing clinical trials involving high? Oops, I lost it. High doses from diagnostic CT examinations. Retha, I don't know if you've got anything to comment on that, understanding you're not a clinician.
Yeah, so I, in fact, was starting to type an answer to that question, and I was trying to understand, what the question was in terms of when reviewing clinical trials. Is the question in terms of looking at this for potential risks versus benefits, in terms of designing trials, or a little bit more clarity in the question would help.
Yeah, okay, thanks very much. Maybe that'll come along as we're going through these. So another question, Claudia, perhaps you could address. So how do the results that you presented compare with those in ICR publication 80, which I think indicate the threshold of 100 millisieverts for IQ damage after in utero exposures?
Yes. I mean, we also have done in our lab some studies about really low dose radiation, and it's really not only in the embryonic state but also in young mice that when you have repeatedly exposure, even at very low doses, 10 milligray, quite impressive effects, at least in the hippocampus area. I mean, showing that these really proliferating compartments with a lot of stem cells, progenitor cells, are extremely radiosensitive. I mean, it's clear single exposure with 10 milligray, it's really hard to show significant, statistically significant differences. But if you use repetitive exposures, you can really show that that you have these effects. So I think this is a discrepancy also to what is, yes, already published by ECRP or something, but we can really see it's published. I can give the literature that when you have even this dose of 10 milligray, but repetitive exposures, then you have these effects. I mean, but it's not the clinical aspect of really impact on cognitive impairment, because this is, of course, another problem, how to study these really minor differences, especially in mouse models, but also in clinician studies. It's a problem. But when you just look at the biological level, you can really show significant differences.
Thank you very much, Claudia. I hope that's answered the question sufficiently. I rather think it has a very thorough answer. So Carl Magnus asking, are there any thoughts on doing a new Quantec summary on the basis of the report that our draft report? Since a lot of treatment modalities, fractionation, particles, immunotherapy, etc., have changed since Quantec. I have to admit a bit of ignorance here because I'm not entirely sure what the Quantec summary is.
It's radiotherapy toxicities.
Okay. So that sounds
Catherine
like
West.
you.
Catherine
Yes.
West, are you there? I'm not sure if Catherine.
There's no point in saying yes when I'm muted, is there?
Yeah. It's a question about Quantec summary.
Yes. No, I heard the question. I think the people involved in Quantec they are the people to revise the Quantec recommendations. The Quantec provides the dose constraints for planning, and the information for the dose constraints could be revised from information that comes out from clinical trials. Whether you can, so it might, and maybe the way dose planning is going is that there will be sub-regions. So, for example, some of the work is done using modern deep learning techniques, AI approaches, that you can identify, for example, a sub-region to the base of a heart that's really going to increase your risk of toxicity following radiotherapy. So it's about getting sub-regions. I don't think this is the place for that, but
okay. Well, hopefully those that develop such summaries might take note of what we've found and consider whether
I find it's very unlikely that people involved in quantum radiotherapy would read this report.
Okay.
But if you feel, if it's an omission not to have mentioned Quantec, so I noted somebody mentioned NTCP, the normal tissue complication probability models, which are being used in the Netherlands to determine the choice of proton versus photon therapy. And I'm at the moment writing a sentence that mentions NTCP so that this community doesn't come across as ignorant of those things. And perhaps I could make a note to mention Quantec recommendations again so that the word is mentioned.
That sounds to be a valuable addition and modification. So thanks for the questions and for the response, Kathy. Next up, we have a question from Christopher. Before this report, AGIR 2013 was the best we had. They felt to produce a main conclusion, they felt able to produce a main conclusion that there is evidence that the induction of cancer by ionizing radiations is subject, at least to some extent, to the risk factors as apply to cancer in the general population. And the question is, does this group agree? I don't know. I will. That's not actually a specific question we asked ourselves collectively, to be perfectly honest. But I think it should have been reasonably apparent that in the presentations you've heard that the answer is essentially yes. So I don't know if any others wish to comment. Kathy, did you put your hand up there? Yeah.
Yeah. I think it's a very valid point because we talk about those recent studies where they've looked at genetic predisposition to breast cancer and shown that the risk of second cancers, risk of having a breast cancer following radiotherapy early in your life is increased if you have a genetic predisposition to breast cancer.
Mm-hmm.
So, and that is clearly a development since our earlier report, just because of the people that have developed the polygenic risk scores for breast cancer have looked at so many patients.
Many more, yeah. Okay, thank you again, Kathy. Pedro here is, are there efforts to look at radionuclide therapies as a subgroup of radiotherapy or low dose rate radiotherapy? I think what we've done and what we've presented is undertake literature searches with search terms which were relevant to the different sections. I don't believe we specifically called out for radionuclide therapy in the search strategies. So I think I'm led to conclude that while we didn't particularly look for it, I think the evidence from the radionuclide therapy area, which is on the whole relatively new, is not very abundant at the moment. Okay, next up from Anna. So a question on the confidence tables in the draft. Not always clear to me if the confidence relates to the conclusion or or the factor. For cancer, it seems to be on the factor, but for the other endpoints, it's less clear. Andre, did you want to address that? Because you spent quite a lot of time on the actual methodology. I think it's meant to relate to the conclusion,
Yes.
but the conclusion in relation to the factor under consideration.
Yeah, I mean, we try to apply this matrix to the conclusions that we draw on whatever the risk modifiers, maybe on the endpoint. Now, frankly speaking, Anna, this is a difficult question because I don't have the chapter in front of me. But yes, so I don't really know how to answer, frankly.
Okay.
Yes.
But we will take that comment into consideration.
Maybe Preeta wants to answer.
Preeta, yeah, go ahead.
So I can certainly add for the circulatory diseases, we were talking about the conclusion. So for example, we might have said we are very confident that we have very little evidence on a certain factor.
Yeah, okay. I think perhaps we should collectively return to that to make sure a sort of a consistent approach is being adopted throughout. Hopefully it is already. There's another question, I think, in relation to the competence stuff. In tables such as 6.5, is it not more suitable to state the conclusion and then your confidence and the overall competence scale? The way it's stated may lead to some confusion to people where the table is taken out of context. Okay, Jim, so I think that's a valuable comment, I think, in relation to how we present that bit. Another question here from Jim saying, thanks first. Do you feel that there's sufficient targeted questions arising from this work to be more of a seed to the development of emerging trials and studies? Well, I mean, certainly we do flag in a relatively short chapter a number of recommendations for research. So certainly there's guides. I guess the extent to which these things are taken up is only time will tell. But I think it's also, I hope, clear to those in the audience that on the whole, these are actually quite difficult studies to undertake. No, sometimes, and if we take some of the emerging endpoints like circulatory diseases and cataract and cognitive impairment, it takes a long time to identify with confidence the main effect of radiation exposure, let alone then delving into subgroups or factors that might be influencing that response. So they're big, long, and complicated studies. So probably it's going to take some time before substantially new evidence will be available. Gloria Maris, was there any research on protective effects of probiotics from radiotherapy effects in the human studies? I suspect as they're not there, the answer is no. But Andre, do you know?
No.
No. Okay, so that's clear. Martin asking about a cataract question and dose thresholds. Can the threshold be defined as a cumulative radiation dose? Has there been any attempt to describe the dose response function in the mathematical function, or can LNT be applied? Nobby, you may wish to comment, but I think I would like to flag first and foremost that our report wasn't specifically looking, or our terms of reference were not to look at the cataract dose response in detail. So we have not undertaken that. But Nobby, is there any comment that you might like to make in relation to that question?
Yeah, thank you very much. So 0.5 lay recommended in the ICP publication 118. It's independent of dose rate and indeed defined as a cumulative radiation dose over life, as well as the acute exposure. And I don't think we have formulated it in a mathematical function. And as far as we classified cataracts as a tissue reactions, LNT model cannot be applied. But discussion is underway in the task group 1 to 3. That's all. Thank you.
Yeah. So thanks, Nobby. That's it is a question under consideration by ICRP more generally, but not specifically the work of this task group. Then Mark's asking again about the uncertainty and confidence assessment approaches. Did I understand from the second talk, Andre, of yours, that the IPCC approach was not always usable? From the table presented on cancers, it looked like
it was usable for us in TG111, but the guidelines that I talk about is apply to all future task groups. And it's as I showed in TG119, for example, they said it's better to use Powell's principle.
Yeah. So I think we've the uncertainty working parties sort of tried to get a sort of a flexible, maybe you might even call it graded approach to how uncertainty is assessed and confidence is presented. So so having a range of tools available, I think is thought it will be useful in the future. Then we have a question: what are considered the main significant changes or updates from this work compared to the current evidence base? Or does it lend towards identifying more of the don't know and what we think domains to identify areas of research? Well, I think there is that aspect of this. There are evidence gaps, and there's evidence areas where evidence is relatively weak, and evidence could be strengthened in those areas. But there are some areas where we are, have that high level of competence, a very high level of competence. So I think having sort of interrogated the literature very thoroughly, we have sort of come up with some consensus about what we do know as well as what we don't know. And we try to flag what we don't know, both what we don't know and what we do know. Another question from Rick: I would guess that the impact of iris color will be very radiation dependent. The melanin will have much more impact for low energy photons. So this, I think, is in relation to cataract again. So I don't know, Nobby, would you like to address that one? I don't know if we have much data.
Thank you very much. Thank you very much. So I mentioned that white skin tone modifies somewhat radiation effects on cataracts, and white skin tone is associated with a lighter iris color, which contains less melanin, more less protective for UV and other perhaps light. So, and the interaction between UVB and ionizing radiation may be interesting for further investigation. Thank you very much, Rick.
Okay, thanks, Nobby. Sorry. So actually, Nobby, another one for you next from William. Oh, Bill, can you comment on medical countermeasures for radiation-induced cataracts following both low and high LET exposures?
Oh, thank you very much for questions. I think there are animal model studies and cell biology studies, but I don't think there is any clinically applied drugs tested and so on. We have mentioned basically that is an antioxidant kind of things. Thank you very much.
Okay, thanks, Nobby. So next up question: to what extent do genetic predisposition and lifestyle factors, for example, smoking and dietary habits, modify the risk of developing cardiovascular diseases and cataracts under long-term environmental exposure to low-dose radiation? Well, I might return also, Nobby, to you and to Preetha, but I think Preetha in particular highlighted that the strength of evidence from the environmental exposures in relation to cardiovascular is relatively weak. So I don't know if either of you would like to add to that.
Sure. So I'll talk about the cardiovascular disease and then hand over to Nobby for cataracts. Certainly, I think that area of the environmental exposure to low-dose radiation is where the evidence is the weakest, particularly in terms of genetic predisposition. The little that we see has been much more in the high-dose cancer radiotherapy studies. So it will be interesting to look at that in some of the lower dose studies.
Yeah. Thanks, Preetha. Nobby, anything from you on that?
Yes, so smoking is related with radiation risk for cataracts, not in all papers, but some cohorts. And for diets, I don't have really knowledge, but as far as I remember, so NASA studies and NASA astronauts studies shows modifying effects of a diet and for the risk within the astronaut. Thank you.
Yeah, thanks, Nobby. So there was a bit of a follow-on question, but I think we covered that. Another from Rick here. Early onset cataracts are threshold in nature, and late cataracts more linear in nature. Since in operational protection, the threshold is unlikely to be reached. Hopefully, does the ICRU change from CVET to grey for eye doses make sense? Surely it'd be better to retain CVET rather than grey. Rick, that's not a question for this task group. That's a question for others to address. So I'm going to not ask anybody to comment on that. Sati, gone to Satyev. There is a strong belief that radiation causes congenital abnormalities among people in contaminated areas. Why it was not included in the review? Because of belief that there are no congenital abnormalities. So this would stem back to the terms of reference for the task group, and you will have seen that the remit was very much on the somatic effects rather than effects in offspring or future generations. There is a ICRP task group looking specifically at risks of exposure in utero and to future generations. So I think that would be addressed by that task group. I can't remember the number of it. It might be 122. But if you consult the ICRP website, you'll see that there is active work in that area. I see we've just turned past 2 o'clock, but we've maybe got time to try and knock all these questions off the list if we don't add any more. How do genetic variations and regional lifestyle factors modify the risk of circulatory disease and cataract following prolonged exposure to low dose radiation, specifically addressing the high doses observed in rural cohorts residing near former nuclear testing sites? I think we've covered that question essentially in the answer to the previous one, so I won't dwell on that given the time. Laura's asking, given the current focus of ICRP on individual sensitivity, isn't the mupalatins cohort an underestimated resource for understanding how genetics and lifestyle modify risks from chronic low-dosage environmental exposures, which differs fundamentally from the acute exposure data of the lifespan study? I think we can agree that the exposure pattern between the two cohorts are clearly different. I think that the work that we've undertaken didn't identify many significant studies of relevance for the report we wrote, but it's a useful flag, Laura, thank you, to have to keep a lookout for. And then the follow on, how can we better integrate the findings from St. Palatins in the ICRP framework? I think that's largely the same point, that we will continue to monitor stuff coming from semi-Palatins area studies for sure, and I suspect there are some, but not many available. I can see one hand, so I'm going to do one last hand, and then I'm going to wrap up, I think, if that's okay. So, Kevin, did you want to ask something? No? Okay. In that case, I would like to thank the speakers, particularly, and all the contributing authors to our draft. It's been a long and arduous task, completed admirably by a very able and very dedicated writing group. So thanks to all, including mentees who are not lesser members of the task group, but integral and essential components. And also I'd like to thank those of you who've taken the time to attend today. I hope you found it useful and informative. It's a topic that I've heard quite a lot of discussion about in various meetings and so forth, so it is a current topic. I think we've had some useful feedback today, but don't forget that the consultation remains open for the best part of a month, closing on the 1st of May. So do submit written comments, should you wish, in the through the MCAP website. So thank you all very much, and take care. I hope to see the final report being published in the not too distant future. Thank you.